Let me show you. Last two topics, all right? Subatomic particles we're going to talk about today, and briefly the periodic table. It's very simple. You need to know that, right? So we're not going to do any calculation with atomic masses, moles, all right? That is the part that we are not doing. Therefore, the mastering chemistry for chapter 2 is very little, only 7 problems, right? So bulk is coming from chapter 1, right? So therefore, finish them before, I think, October 2nd, right? All right. Okay. Now, we talk about the existence of atoms, that we have evidence based on microscopy. There are several branches of microscopy. One is optical microscopy, using the light to magnify certain objects, under the microscope. But the light only gives a micrometer resolution. Micrometer means you cannot see objects smaller than micrometer with light. Therefore, we had to find out other ways. The other way is to get the different techniques. Scanning probe microscopy. We'll talk about it here. One of them is scanning tunneling microscope. There's a current passing through from the tip or the cantilever, so you can map the surface features. The atomic force microscopy is same thing, but there's no current. Very sensitive cantilever. It will, as it comes close to the surface, it will be repelled by the atomic forces of the surface. Therefore, this surface is mapped just like that, and give a bigger image, right? Surface features according to whatever this cantilever find on the surface. Just like a blind person using his cane, maps the roads and the obstacles on the way. He does the same thing. Other one is electron beam. Electron beam is one similar to that is scanning electron microscope. It uses a beam on the surface and look at the reflection from the surface, the reflected electrons. Those are intensities of those reflected electron beams show the surface feature where there's some height. There are going to be less electrons. If this is flat, there's more electrons. So therefore, it could get the surface features. All these three techniques goes to a sample in a linear wave, 1 nanometer at a time, like that, even few nanometers. The transition method, electron microscope, is the analog of optical microscope, where the light is passed through an object, right? Then you can see the image. Just like a regular microscope, need to have light passing through the sample, right? You put a light in there, right? Okay. In here, electrons are the beam. So electron gives nanometer resolution. Electron beam is different from light beam, visible light. So the resolution is something to do with the light or the beam you are using. So light cannot achieve nanometer resolution. Therefore, transmission electron microscope, which is the analog of optical microscope, has been used. All right, we talked about these in our last time, and we also talked about that the early chemists, we call alchemists, started doing experiments mainly to convert the lead to gold or precious metal, non-precious metal to precious metal, and something useful. They always trying to find something useful, just like the chemists today. I mean, we are not doing anything, all right? So we only try to find something useful, right? So we are still alchemists in a way, right? So alchemists didn't follow scientific method exactly, but they became scientists eventually. So based on their observation of chemical reactions, they saw a pattern in their observations. When two compounds, when two elements reacted together, they begin to see the mass is conserved. Mass before and mass after. That's the law of conservation of mass. Then when two different elements combine to form a compound like carbon dioxide, the ratio of masses between these two elements are always same, right? So that's called the law of constant or definite proportions, and that's a pattern, okay, in the data. And then multiple proportions, right? When two elements combine to form two different elements like carbon monoxide and carbon dioxide, there's one element, the mass is multiple of one, multiple of 2, 3, 4, right? For example, in carbon dioxide, the mass found in carbon monoxide per 1 gram of carbon is twice multiplied by 2. That's called the multiple proportion. So therefore, we have observations and summarized, and laws are written, pattern in observation. So this is the mass of conservation of mass. Right. Now these are the laws we already wrote down yesterday, the other day, right? Law of conservation of mass. What is the other one? Law of definite proportions or constant proportions, or law of multiple proportions. Remember? Okay. Now let me explain a little bit more, those who haven't heard about it. Mass is neither created nor destroyed. In a chemical reaction, this is the pattern. If you take a chemical reaction, you take the masses of the reactants before you do the reaction and measure the mass of all the products together, right? That's the same. That means atoms are not, basically atomic theory explains because atoms are still there, right? Chemical reactions are recombination of different elements. For example, this is a data that shows the pattern. 4 grams of hydrogen and 32 grams of oxygen gives always 36 grams of water, right? So if you add 4 plus 32, it is 36, okay? Now, constant proportion is like this. If you take water, 4 grams of hydrogen and 32 grams of oxygen is found, this ratio, simple ratio, 1:8. It's a constant proportion, definite proportion. It is always found in water, no matter you find water, okay? What is the ratio for oxygen to hydrogen to oxygen? 1:8, right? See, these are reflected in atomic proportions, right? Because that's masses could be converted to moles. Moles are certain number of atoms, right? The law of multiple proportion is dealing with two elements, carbon and oxygen, forming two different compounds. Now, you might think two elements together, only one compound. No, it depends on the proportion, right? Like carbon oxide, carbon monoxide, only one oxygen, carbon dioxide. For example, 1 gram in carbon monoxide contains 1.33. That's constant proportion in carbon monoxide. But if you look at constant proportion in carbon dioxide, it is 2.66, 1 to 2.66 here. What it tells you is, if two elements combine to form, two different elements combine to form two different compounds, the first element, certain number of gram of first element in each compound, and if you take the mass of the second element in each compound, there's a this is a multiple of 2. Yeah, 1.233. You see that? That's called multiple proportion. Multiple proportion deal with several compounds formed by two different elements, like hydrogen peroxide, H2O2, right? Water, right? So that is a pattern in the observation. Now we are describing the scientific method, right? Okay. If you didn't understand this, in the atomic level, why there is 1 or 2 to that's multiplied with this carbon monoxide multiplied by 2 is 2.67. Why you get 2.6? That ratio. Atom has a mass, right? There are 2 oxygen atoms there. There's only 1, right? That explained by the law of multiple proportions. Therefore, this is the prelude to getting the idea. We haven't seen the atoms, though nobody saw atoms. But you begin to see there's a particle, all right? So that's the prelude to Dalton's atomic theory. Now that's what I explained here again. 1-to-1 ratio of carbon monoxide, 1-to-2 ratio in the carbon dioxide. The combination can be represented as a ratio, for example, right? Okay. What are the patterns? I'm asking this question you answered, right? What are the patterns? Law of conservation of mass, which is mass before the chemical reaction is the mass of the reactants before the chemical reaction is equal to mass of the products after the reaction. Then second one is law of constant proportions in a given chemical compound, ratio of masses, simple ratio of masses of each element is constant, 1-to-8 in water, right? Then law of multiple proportions, when a 2 elements combine to form 2 different elements, there's a multiple of weights of the second element, right? Indicating that ratios are different, but they reflect 1 atom and 2 atom in the other case. That's the multiple proportion. Now this is the idea. After this came, this is the scientific method. Remember we have observations, right? What do you come up with? Hypothesis. Trying to explain your observation and the laws, right? What was the law? Dalton's atomic theory, all right? Dalton's atomic theory is the law we came up. So Dalton's atomic theory, what law we came up with? Dalton's atomic theory. Now let me tell you and show you now, like we said before in chapter 1, scientific method has theories. This is a theory. Theory could have postulate. Postulate is separate paragraph describing different features of the theory, right? Model. What is it? There are 4 postulates in the Dalton's atomic theory. First is, we're going to write down later. Just we write down the atomic theory here, okay? Okay. Now, Dalton's atomic theory has postulates. What is the first postulate? Matter, say that again. Somebody said something.
All matter is composed of atoms.
All matter is composed of tiny particles, all atoms, indivisible, right? Smallest particle. The Dalton assumed, like Greeks before him, that atom couldn't be divided. They didn't know subatomic particle, right? Right, this is the idea. All matter is composed of atoms, the smallest particle of element that take part in a chemical reaction. All right. Dalton is a chemist, physicist, right? What is the second postulate?
Can be created or destroyed. Atoms can be created or destroyed.
Right. That I wrote down as a fourth one. On the order, right? First one is this, then the second one is all atoms of element are identical. All right? So we had to define what it is. An element is defined by the different atoms, all right? Each element has different atoms, right? They have different masses, all right? We talked about it. So all atoms of elements are alike. That means Dalton didn't know there are isotopes, remember? Now we know there are isotopes. The element is defined by atomic number, right? Not by just the mass. Mass number is not the defining criteria for the element. What is the other one? Whatever the atom is neither destroyed nor created is the fourth one. The third one define constant proportion, describe the constant proportion and multiple proportions. Right, how you define that is, explain that is, compounds are combinations of atoms of two different elements, right? Compounds. In fixed ratio, a compound has atoms of 2 different elements in fixed ratio. If 2 elements form 2 different compounds, then that ratio is different for each different compound, right? That's the idea. Let's see how they wrote it. Compounds are a combination of atoms of 1 or more elements, all right? The relative number of atoms, each element is always same. All right, relative number, even carbon dioxide, if you take carbon dioxide and carbon monoxide, relative number of atoms are carbon 1, oxygen 1. Carbon dioxide, carbon atom 1 carbon atom, 2 oxygen atom, right? Therefore, there are 2 different compounds. So they define that, this statement, third postulate defines. Now atoms cannot be created nor destroyed. Now this explains conservation of mass. If atoms are destroyed, then the mass should be different, right? The chemical reaction is defined by this combination of atoms. But atoms never change in chemical reaction, except in nuclear reaction, right? We're talking about chemistry here. So these are the 4 postulates of Dalton's atomic theory. Now, can you write down those here? Okay, we go on over each one. So first one is atom is the matter is composed of smallest particles called atoms, right? And the second is, I mean, you can in your own words. Second is atoms of an element are identical. Third one is atom combined to form compounds. Compounds with constant proportions, right? Or multiple proportions, given two different compounds. Fourth one is atoms are neither created nor destroyed in a chemical reaction. They are just simply different combination of atoms. Okay. Now, if we had to modify this theory, this is Dalton's idea. What do you write to include everything we know today? All right. How do you define it? It's not the smallest particle of matter, is it?
No.
Like the matter is composed of atoms which have subatomic particles, right?
Yeah.
It's a collection of subatomic particles of neutrons, protons, and electrons, right? Now, matter is composed of atoms, which is collection of neutrons and protons in a nucleus and electrons traveling around the nucleus, all right? So we can call it atomic number and all that stuff, right, later. And that is, you have to include a sentence here. Composed subatomic particle I would say neutrons, protons, electrons. Neutron has no charge, electron has neutron, right? Proton, electron. Then the second hypothesis or the postulate of the Dalton atomic theory, is it true? Atoms of elements are identical? No. So, atom of an element, how do you define it? Is defined by number of protons, right? In the nucleus, that's the atomic number, and they could have different number of neutrons, right? They could have a different number of neutrons. Okay, electrons, number of electrons are same as number of protons. How many of you heard about that? Number of protons and the electrons are same as protons, right? Okay. Now the third one is, and the fourth one hasn't changed. The postulate, third postulate, atom combined make elements, elements, two or more elements combined make compounds, and they do that in constant ratio or multiple ratio, remain the same because it didn't change. And the atoms are neither created nor destroyed, all right? That means atomic structure remains intact, all right? But only atoms remain intact except for redistribution. Of electrons. Now they will share electrons, they will gain electrons, you remember? So therefore, atoms are neither created nor destroyed, atoms remain intact except redistribution of electrons outside the nucleus. Valence shell, I mean, if you wanted to be specific, okay? Atoms remain intact except redistribution of electrons. Okay, these are the modern atomic theory. Much hasn't changed. Now we wanted to look at how we change the Dalton's atomic theory. What evidence we got? Remember, in science, we always keep doing experiments, right? Further experiments. So the further experiment sometimes don't explain everything. The Dalton's atomic theory didn't explain everything. Now we had to modify it. It became modern atomic theory. All right. So that's how a theory works. Now the first evidence that atom is not divisible or consists of subatomic particles came from radioactivity. What is radioactivity? Radioactivity is a phenomenon. Can someone explain to me? What is radioactivity? Say that again. Right. Certain elements are not stable, especially one with the light typesetting, TC, technetium, uranium also not, but they are still present, actinium, elements after bismuth, okay? Polonium, astatine, radon. How many of you heard about radon is bad for you if your basement have a lot of radon, right? Radon is radioactive, right? So therefore it can cause cancer and other things. All right. What is radioactivity causing cancer is something to do with, could you check if still the red button is there? Yeah, it is.
The red light is blinking. Oh, that one's there.
Okay. Okay. What happened is, they emit radioactivity is due to decay of unstable elements to stable elements. For example, uranium decay to lead, all right? Because lead is more stable than uranium. Now, when they do that, they emit radiation. That emission of radiation is called radioactivity, okay? Radioactivity. So, Becquerel, found this. He had a sample of uranium sample from somewhere in a mineral sample containing uranium. So he put it in his lab, and he had a photographic plate, next to it. Then all of a sudden, this photographic plate was exposed. He goes, well, what happened to my photographic plate? He must have been mad. Then he couldn't figure out. each time he keep photographic plate, he does. Then he remove this mineral sample, right? Okay, that's a discovery, right? Itself. So he found out that certain radiation, right, emitted by this sample, uranium sample, flogged the photographic plate. All right. Now after that, it took some time. You heard about this Marie Curie and Pierre Curie. They discovered two elements. I think when I was a small, not a small, when I was in high school, I got a book on their life story. You know, that's very pretty kind of. Maybe that's why I'm a chemist, right? No, I don't think about that. But it's very inspiring, all right? How they did this discovery from another iron, another earth sample. They found polonium and radium. Those are radioactive too. Now, one thing about this is radioactivity was curious phenomenon. Nobody knew what radioactivity was that time. They know elements are being changed, decaying. What is radioactive decay? There are three ways an element can decay. One is alpha radiation. Alpha is a helium atom can come out of the nucleus. Helium nucleus can come out of the helium nucleus is 2 protons, 2 neutrons, right? Mass number is 4. All right, they are helium. It's a positive particle. Alpha is helium. Like you need to learn this a little later. When you have an element, this is called mass number. We call it A. C, that's the positive X. This is the charge. This is the number of electrons that's been removed from the atom. All right? Okay. Helium particle is a nucleus, helium nucleus. Because helium atom has 2 electrons. They stripped off 2 electrons, you get a alpha particle, right? This 2 plus, okay? That you can write down that alpha particle is helium. Now this is a heavy particle, all right? Heavier. Now the next way to decay is beta radiation. It's a negative charge. It's an electron coming out of it. Now what happened is when a nucleus, we think neutron is a combination of that, proton and electron. Okay. When an electron comes, or beta particle comes out of the nucleus, the atomic number increased by 1, all right? It changed to a different element, all right? We talked about it. Atomic number is the one that decides, right? So when the helium is emitted, atomic number is reduced by 2. Atomic number is here. 2 atomic numbers, helium. So you can successively, repeatedly, okay, you can remove these particles, alpha, beta, right? And bring down change the nucleus, right? Uranium would become lead. Now the gamma radiation is, there's no charge, it's the energy associated with destruction of this radio unstable atom, all right, gamma. Now out of these, gamma is a highest frequency electromagnetic radiation. You know what I meant by that. electromagnetic radiation has
More waves per second.
gamma, X-ray, visible, UV, visible, IR, radio waves, microwaves, radio waves, right? That's the highest. So it penetrates the most, right? The most damaging. The next one is most damaging is beta. Because it's a small particle, it will pass through you several centimeters, right? But the alpha particle being heavy, just like a heavy thing cannot go into the wood or the hardness of the material. So they are least penetrating out of these is this, less harmful. Therefore, gamma is the bad one. Now, this one has a positive charge, this one has a negative charge. How do you know? I will show you how to find the negative and positive charge in a minute. Oh, okay, here. If you put an electrical field, beta get attracted to the positive plate and alpha get attracted to the negative plate. And gamma just passes through without being affected, right? So that's how you identify. What are these forms of radiation? Okay, answer to B is this, answer to A is this, alpha, right? You don't write that one. Alpha particle, and this is the helium nucleus. B is electrons. And C is electromagnetic high energy. Electromagnetic radiation. Gamma. All right? Yes.
So this radiation takes place because the element splits, like the helium splits?
Right.
Or the electron
This
splits?
radiation is the form of energy, right? It's not thermal energy. Thermal energy is a microwave. Normally that when a chemical reaction takes place, heat is the one, that creating microwave and converted to heat, right?
Yeah.
The huge amount of energy is released on a nuclear reaction. How many of you know that nuclear reaction produce enormous amount of energy? So that energy is very high, okay? So that's highest form of energy, like gamma radiation. That's why it's very high, okay? The chemical reaction thermal energy, microwave or something. Which of the following radiation, alpha, beta, and gamma is most harmful? Gamma. Okay, it causes cancer, it can dislodge base pairs in your DNA, right? Create mutant cancer cells, all that stuff. Anything can cause cancer, chemicals too, right? Okay, Thomson discovered the cathode rays. This cube here is, okay, let me see, that's a cathode. I had to, okay. This is what exactly Thomson did. Depend on where you connect. Okay, that's the cathode, all right? Negative end, positive end, all right? This is called cathode rays. this is a screen made out of zinc sulfide. It fluorescents, it shines, okay, when you do the thing, like turn this on. Okay, for example, if I apply a magnetic field to this, magnetic field positive here, oops, man, I'm negative. What happened? That time it went down, right? I don't know. I might discover something, you know? Okay, for example, this magnetic field also deflected, all right? But the whole idea is if you put a positive plate here, negative, it goes up towards the positive place. Therefore, electrons are negatively charged. Right. Now, I want you to summarize some of these stuff. Thomson measured mass to charge ratio. All right. This is Coulomb, that's the mass. The Thomson. I will say J, right? J. Thomson. Millikan. Mulliken or Millikan. Mulliken, I think. Got this. I think 5.16 here. 1.61. That is negative 19 coulombs. Negative charge. That's the charge on the thing. How do I remember? I noticed that it's 61 and this has a 1 in there, you know? All right? We'll check. I mean, I may have. All right. So I'm not going to go through this too much because most important thing is he calculated the charge to mass ratio. Cathode rays are the beams, fluorescent screen, that's called fluorescence. Okay. So this is found in, regardless of this phenomenon is found regardless of the gas you put in. Helium, hydrogen, everything has this. Therefore, all the elements have electrons. That's the first subatomic particle. They are negatively charged particles. Thomson showed electromagnetic field deflect here like that. Mass to charge ratio 5.60. I put a 1 in there. I don't know why. Maybe I was too accurate. I think this still holds. 5.6 10 to the negative 9 grams per coulomb. Coulomb is the unit of charge. Now in this case, he didn't know what's the mass of the electron. So to find the mass of the electron, you have to find either charge of the electron and plug in this ratio, right? Then calculate the mass. Therefore, there's a race to find the charge of the electron. That was won by Millikan, right? Millikan found out that charge is that. Okay, I will talk about it. How did Thomson know that every element has electrons? Every element in the gaseous form in its cathode rays produce cathode rays, right? Rays that are emitted from the cathode. How did Thomson know that it has a negative charge? It deflected by towards the positive plate of the electrical field, right? Okay. Okay, now let me explain this. I don't want to get into high-level details of how we do this experiment, but I will tell you what. Millikan Millikan, right, not millikan. Oil experiment, how did he remove electron from atom? I will show you how he did it. In the Millikan-Roy experiment, where did some electron removed from atom end up? He removed electron from somewhere, from the atoms. In the Millikan oil drops experiment, some oil drops have multiple of this charge, electronic charge, what we call it. Okay, this is the Millikan oil drop experiment. He sprayed oil drops, and there's a hole, it drops, okay? Now he had a microscope, and he had an X-ray source. Remember, he had the X-ray source and the microscope and not in the line, you're not going to look into microscope with X-rays coming into your eye, okay? Now, when the X-rays hit the oil drops, there's a gas in here. There's a, just like here, there's gas, which has atoms. These X-rays knock off electrons from those gas particles, right? Like, for example, hydrogen or helium. Assume helium. So then when helium gas loses the electron, electrons get trapped on the oil drops. There's a chance certain oil drops could have a negative charge. Some the oil drops could have more than 1, 2, 3, 4 electrons, right? So what he did was, he fixed, this is the electrical charge here. He adjusted the electrical charge, electrical field, so that these oil drops could suspend in the middle of it. So he can calculate the electric charge based on physics, that how much charge is on the oil drop. So he found out that some oil drops, you had to increase the charge, electrical field, to get them in the middle. Some have 2 oil drops, some have 3, then more electrical field change. All right, that's how we did it, how he did it. Okay, now we go back to here. Answer this question, all right? Hey. I would have been here for you, okay. In the Millikan oil drop experiment, how did he remove electrons from atoms?
The electrons would suspend.
Ionized radiation.
X-ray.
Yes.
X-ray source. So the X-rays will ionize, okay? The gas in the chamber, all right? All right. In the Millikan's oil drop experiment, where did some of the electron removed from atoms ended up?
Probably on the positively charged plate.
Say that again?
I don't know. I guess the positively charged plate wasn't they attracted it? Like when
They could have, but we are looking at the oil drops with the microscope, right?
Right.
On the oil drops. Some of them ended up in the oil drops. Then he changed the magnetic electrical field, right?
Right.
Suspended them because the bottom plate is negatively charged, right? So it will repel, right? So if you increase the field, it will even go back out, okay? So like that. In the Millikan's oil drop experiment, why was some oil drops had multiple of these, of charges? Because if you have electron charges 1.6 10 to the negative 19, right? If you have multiple of them, that means
Well, all the atoms have a whole number of electrons, so you count the charge and when you measured the charge of each electron, it was all whole number multiple.
I'm talking about the not atom, whole drop.
Yeah. That's what
So why it has multiple charges? Not, okay. Do you understand that? If you had only one of them, charges on the one oil drop, how many electrons it had? Charge of the electron is 1.6 10 to the negative 19, right? So if you had one of them in the oil drop, how many electrons? One, okay. If you have multiple 2 times that, that means the oil drop had 2, all right? Then if you have 3 times that, that may be the problem you are not looking at. Multiple means, all right? Their oil drop had 3 left. But this consistently showed that electronic charge is negative 1.6 10 to the 19, right? So after he got that, Thomson calculated the ratio is 5.6 days. How do you get mass of the electron? Okay, here is the idea. Mass divided by electronic charge is 5.6, 0 to the negative 9. And electronic charge is 1.6, 10 to the negative 19, negative 5.60, 10 to the negative 9. So mass of the electron is what? 5.60, 10 to the negative 9, multiplied by 1.6, 10 to the negative 19, which is, can you do the calculation? I don't have the calculator today. Oh, I do.
It's right in front of you.
Okay, what is the answer? I don't know what it is. Answer is 9.10, 10 to the negative. That's the mass of an electron. Did you get it?
No.
Very close to it. This is the accurate value.
I didn't even come.
No.
What do you got?
What's on the board?
Where's that from?
The ensign 9 multiplied by,
Why did you do something?
Yeah.
Yeah, that's a nice question.
negative 19, okay? Okay. That you got?
No.
6.
All right.
I have a question.
Now the modern value is this. See?
So what?
Yeah.
When you thought when you multiply anything with the power, you add the powers. How would you get negative 28? I guess negative 10.
Hey, I put in my calculator, okay? And I got the answer. All right.
All right, but also, why did you divide 1.6 times 10 to the negative 19 times by negative 5.6?
No, this one is wrong. This is multiplication.
Oh, okay.
Okay.
I did that in dry type, okay? There's no division. That's a mistake, right? Okay. Okay. I cannot change it here. Okay, now look at the value to the so many decimal places now. It's always this crude apparatus, right? Oil drop blowing out, in early 19th, 20th century, they did it. It's pretty good. So you understand that how we discovered the particles. Now after we discovered the particles, what we thought was, Thomson came up with a model. He didn't know there was a nucleus. He thought electron is a plum pudding. What is a plum pudding? Plum pudding is like a raisins, all right? And the cake and the raisins, like this. This is the cake. The cake is the positive charge. He thought the positive charge is smeared all over the place. First atomic structure was that. But this didn't survive more than a couple of months because we don't even hardly talk about it. So what changed it? We came up with nuclear atomic model, right? Nuclear atomic model is all the positive charge is concentrated in the middle where we call a nucleus, right? Who discovered that? Rutherford, right. What he did was this, nuclear atom. He put a gold foil and shine alpha particles. If this gold foil positive charge is smeared all over the place, all over the atoms, it should go through this like a paper, bullet going through a paper, because everything is smeared out, positive charge. There shouldn't be any repulsion. But what he observed was, some of them directly came back towards the source, even some here. So deflection of alpha particles indicated that there is a place in the atom, okay? This is the plum pudding model. It should pass through, Electrons don't affect that much. But here, if you have a positive charge here, they repel here. According to Rutherford, the positive charge in the atom is concentrated in a place called nucleus, right? All right. Now we know more about it. There are neutrons, there are protons there, right? We came up with the nuclear atom. Who created that model is Rutherford by gold foil experiment, right? Now, I'm going to not talk about this too much. Then a person called Rutherford student, mostly, found out the atomic number. So he was credited for discovery of proton. Atomic number is protons. Then Chadwick found out neutrons. Chadwick is the one who discovered the neutron. Therefore, we have electron, proton, neutron. Okay? Let me go do this. 9.1, 10 to the negative 28. We very close to we calculated it. 1.6. Charge on the electron and the proton are the same. Neutron has no charge. Now, if you look at the neutron and proton, the neutron is slightly heavier than the proton. Why is that? answer to that we discussed in the beta particle production. Remember how we get the beta particle is neutron is converted to proton and electron, right? Therefore, neutron is essentially proton combined with the electron, right? Okay. So, right. So you got the idea about basic structure of atom. Atomic number is the number of protons in the nucleus, or number of electrons in the neutral atom. The number of protons and number of electrons has to be equal for a neutral atom. If you lose the electron, they are not going to be equal. The integer on the periodic table for each element, that integer 3, 4, 1, 2 is on the right top corner. That's the atomic number. How many protons are in the nucleus? The atomic size is very small, and the nucleus is even small. If you have approximately 10 to the 10 meters, the nucleus size, the atomic size, is negative 15. What I heard was this. If you have a nucleus here, where you find the electron in the hydrogen atom, where would you find it? It's in your dome, somewhere there. In the I-20, it would be in the gram loop, 5 miles away. See, if you have a scaled up, everything distance-wise, all right? If you have a nucleus, then your electron will be about 5 miles away, if you scale up everything to miles, right? 10 to the multiplied by a factor. What are ions? Ions are charged particles produced from atoms losing or gaining electrons, right? Gaining electrons is called an anion, cation, right? All right. Now we show. Do you guys sign the classroom? Everybody? Did you get it? Okay. Now, atoms of an element has a symbol. We already know how you give a symbol. Hydrogen. Hydrogen have 2 isotopes, 3 isotopes. This is hydrogen 1, we call it hydrogen 1, hydrogen 2, hydrogen 3. Sometimes hydrogen is the only element which has its own names for isotopes. What is the hydrogen 2 called? Deuterium. Tritium is the third one, hydrogen, deuterium, tritium. So when you have a symbol, this is called mass number. Mass number is sum of the neutrons, number of neutrons plus protons, right? Mass number. What is the atomic number? This is the mass number. Sometimes we write down here, sometimes we write, the C is the atomic number. All right. If you have an element, A is here, Z is here, charge. It could be positive or negative. Okay. That's the symbol is the atomic symbol. For example, carbon has carbon 12, carbon 13, carbon 14, 3 isotopes. Alright. Carbon 12 and carbon 14 is radioactive. So this is the carbon 12. Normally we write down this is because we cannot type, the same place. Integer representing the mass of the